Hello everyone, this is Team Satvik Kadian and Sanskriti Goyal. Here we are doing the assignment one of the course ES116, which is the Principles and Applications of Electrical Engineering. So moving on to the task one of the assignment, which is the piezoelectric sensor analysis, in which we plot the magnitude response and the phase response of the piezoelectric sensor using the signal generator and the oscilloscope and the circuit elements, in which we identify the resonance frequencies and then calculate the quality factor for the respective resonance frequencies. And the task two is the photodiode analysis, in which we again plot the magnitude response and phase response of the photodiode using the same apparatus and determine the 3 dB cutoff frequency. So now we move on to the experiment part of the task one.
So this is a signal generator in which we set the frequency to 1 kilohertz initially and then amplitude and offset to the 5 volt, and then we pass it to the breadboard. From breadboard we generate two circuits. First we directly pass it into the oscilloscope, and another circuit is made through which we pass into the piezoelectric sensor, and through piezoelectric sensor to channel 2 of the oscilloscope, which gives the blue signal, and the direct input signal is shown by the yellow signal. Now we adjust the frequency using the signal generator like this. And now it shows the different signals, as you can see. So this is the second experiment where we plot the magnitude response and the phase response of the photodiode. So this is the signal generator from which we provide the input to the LED. This is channel 1, which will provide the yellow signal on the oscilloscope. So this is the circuit on which we will work. So now this is the LED, which is the input part from which the signal is generated, and then we connect the resistor in series with the LED, and in front of it we connect the photodiode in such a way such that the maximum light lands on the photodiode, and then we give the 5 volt input from the breadboard module to the photodiode and take the output out of the photodiode to the oscilloscope. This is the oscilloscope. We give a direct connection also from the signal generator to the oscilloscope, which is the yellow one, and one signal is passed from the photodiode to the oscilloscope, which is the blue one. So after setting up the circuit, we keep changing the frequency from the signal generator like this, and hence the output changes. Now we again change the signal, and again the output will keep changing, and hence we take the different outputs and record the signal.
So now we move to the theoretical part of the experiment. In the task one, we had to plot the magnitude response and the phase response of the piezoelectric sensor and calculate the quality factor for the resonance frequencies achieved. So this is the data set which we achieved during the experiment, in which we recorded the frequency, channel 1 BPP, peak to peak voltage for input and output, and we calculated gain in dBs, which is given by the formula voltage gain equal to 20 log to the base 10 V naught by V1. And then we calculated phase difference of input minus output, that is channel 1 minus channel 2 in degrees. So let's talk about the resonance frequencies. Resonance frequencies are the frequencies at which the sensor exhibits peaks in amplitude due to mechanical resonance. The first and the largest peak in the graph is the primary resonance, or the fundamental mode, which occurs at the natural mechanical vibration frequency of the piezoelectric material. And also this is the most sensitive frequency for the sensor. And following it, we get the harmonic resonances or overtones, and the dipole value following the resonant peak. Also, we recorded some pattern in the phase transition, which is that around the resonant frequency, the phase shifts rapidly from 0 to minus 90 or even minus 180, which we will see in the graph in more detail. So this is the graph of the magnitude response of piezoelectric sensor, in which we plotted the gain in dB on y-axis and frequency on x-axis. This one is the logarithmic scaled one, and this is the linear scaled one. As you can see, that around the 200 hertz we get our first peak, and around the 2 kilohertz we get our second peak. So, and now we move to the phase difference graph. As you can see that around the resonance frequencies we get a much more phase transition about minus 90 or minus 180 degree. As you can see that there is shift of shift around the 0 degree line, which is the middle line going passing through the middle. So now we look at the resonant frequencies interpreted from the graph. So at 200 hertz, we recorded the gain of 10.421 dBs, which is the primary resonant peak. And at 2 kilohertz, we recorded 3.676 dBs, which is the secondary resonant peak. Now we move to the calculation of quality factor. Quality factor is given by the resonant frequency divided by the bandwidth, and bandwidth is calculated as the range where the dip of the 3 dB gain takes place. For the primary resonant frequency, we have which is 200 hertz. The minus 3 dB frequencies occurred at 237 in the upper region and 174 at lower region. So we calculated the bandwidth frequency and then we calculated the quality factor, which comes out to be 3.17. And similarly for secondary resonant frequency, there is only right-sided 3 dB dip, not on the there is not dip on the left side. So again we calculated the del F and quality factor comes out to be 2.62. So this is the summary of the experiment one. And also we can see that quality factor for 200 hertz is greater than the 2 kilohertz one, which is also shown in the graph or proven in the graph. As you can see, the 200 hertz peak is more sharp and evident than the 2 kilohertz one. These are the waveforms recorded at the resonant frequencies. The first one is at the 200 hertz and the second one is at the 2 kilohertz. Now moving to the second task in which we had to plot the magnitude response and the phase response of a photodiode and also the 3 dB cutoff frequency. Here also we recorded the same data frequency, input VPP in channel 1, input VPP, output VPP in channel 2, phase difference of channel 1 minus channel 2 in degrees, gain and gain in dBs. So this is the following data set which we recorded. So this is the graph of the magnitude response in the logarithmic scale, and this is the graph of magnitude response in the linear scale. As you can see, the red dotted line marks the cutoff frequency, which we will talk about later. And this is the graph of frequency response. This is the graph of phase response. So the key observations from the graph are that the around lower frequencies we get a flat response, and the gain is almost around minus 29.8 dBs. This indicates that the photodiode is efficiently detecting signals without much attenuation. Then we get a gradual roll off, a slow decrease, and then there is a steeper roll off, which we can again see in the graph. As you can see, first we get a around minus 29.8 or 30, minus 30, we get a constant phase response, and then there is a sudden dip after the 100K to the 1 million frequency. This suggests that the photodiode is no longer able to effectively detect the signals beyond the 1 megahertz point, and the bandwidth of the photodiode likely falls within this range, which is the 100 kilohertz to 1 millihertz, as there is a gradual, there is a steeper roll off. So now we calculate the 3 dB cutoff frequency. So the 3 dB cutoff frequency is the frequency at which the gain drops by 3 dB from its maximum stable value. So the gain is nearly minus 29.8 stable from 100 hertz to 10 kilohertz, which can be considered as the reference gain. And the minus 3 dB point which we get is the minus 32.8, which is minus 29.8 minus 3. So we look at the first occurrence where this gain is recorded. So as you can see in the graph, we marked a red line which indicates that we got the frequency frequency for the minus 32.8 dB, which was recorded as 83 kilohertz. Thank you.